Welcome to episode 7 in this series on differential geometry. In this episode, we'll talk about mappings. Given a function from Rn to Rm, we'll let the components of f be written as real-valued functions on Rn, f1, f2, etc. through fm, so that when we compute f of p for point p in Rn, we could simply write this in the components f1 of p, f2 of p, etc. through fm of p. We'll call these functions the Euclidean coordinate functions of f. A function like f is said to be differentiable provided that its coordinate functions are differentiable in the usual sense. A differentiable function f is called a mapping from Rn to Rm. Next, let's talk about compositions of mappings. If alpha is a curve in Rn and f is a mapping from Rn to Rm, then the composite function beta, which is the composition of f and alpha, is a curve in Rm called the image of alpha under f. In the figure, we're just imagining a simple case where we're given a curve in R, which is just Next, let's talk about compositions. If alpha is a curve in Rn and f is a mapping from Rn to Rm, then the composite function beta, which is f composed with alpha, is a curve in Rm, and we call this the image of alpha under f. Now we define tangent maps. Let f be a mapping from Rn to Rm. If v is a tangent vector to Rn at the point P, then we'll call f star of v the initial velocity of the curve of one parameter f of p plus tv. So p plus tv is a line, and we're considering f applied to that line, which is a curve. The resulting function f star sends tangent vectors to Rn to tangent vectors to Rm, and we call this the tangent map of f. Let's consider the following proposition. Let f be a mapping from Rn to Rm. We'll write the Euclidean coordinate functions as f1, f2, etc. through fm. If v is a tangent vector to Rn at P, then the tangent map f star of v is equal to the directional derivatives of the f1, f2, etc. through fm in the direction of v and at the point f of p. To prove this, we'll write beta of t equal to this curve, the composed curve f of p plus tv, so that by definition f star of v is just beta prime of 0. So the tangent map is the set of points where the coordinates are the derivatives of the coordinate so the tangent map could be written with each of the coordinates of f so we may write the tangent map as being the curve where the components are the derivatives of the Euclidean coordinate functions of f evaluated at t equals 0. This is just the curve where each of the components are the directional derivatives, as we stated, because that's the definition of directional derivatives. Here, of course, beta of 0 is f of p by the way that beta was defined. Next, we prove that if f is a mapping from Rn to Rm, then at each point P of Rn, the tangent map f star sub P from the tangent space of Rn at the point P to the tangent space of Rm at the point f of P is a linear transformation. Indeed, we don't need to say much about this proof because it actually follows the previous proposition immediately. All we need to do is apply the fact that the directional derivative is linear. Next, we consider the following corollary. Let f be a mapping from Rn to Rm if beta equals the composition f with alpha, which is the image of the curve alpha under f, then beta prime is equal to f star of alpha prime. To prove this, we write beta, which is equal to f of alpha, and then in components, each of the components are fi of alpha. Then, using theorem 7.5, we know that f star of alpha prime is equal to the curve where each of the components are the directional derivatives of the fi in the direction of alpha prime. By lemma 4.6, we can rewrite each of these components, these directional derivatives, as just proper derivatives of the curve alpha evaluated at beta of t, and this is, by definition, beta prime of t. Next, if f is a mapping from Rn to Rm, then next we will write uj as the natural frame fields of Rn, and U bar K as the natural frame fields for Rm. Then if F is a mapping from Rn to Rm, then the image of the natural frame field vector fields Uj under F star are equal to linear combinations of the natural frame fields U bar sub I of Rm, where the coefficients will be these partial derivatives of the components of F. This follows from proposition 7.5, where we use the fact that partial Fi, partial xj, is the same as the directional derivative of Fi in the direction of Uj. Finally, we define regularity in the following manner. A mapping F is regular provided that at every point P of Rn, the tangent map F star sub P is 1 to 1. We state the following theorem without proving it. Let F be a mapping from Rn to Rm, and we'll suppose that this mapping is between Euclidean spaces of the same dimension. If F star sub P is 1 to 1 at a point P, there is an open set U containing P such that F restricted to U is a diffeomorphism of U onto an open set V. A diffeomorphism is a function whose inverse exists, and that function and its inverse are both differentiable. We don't expand on this point here because this is more of an analysis topic and less important to prove in differential geometry. We call this theorem the inverse function theorem, since it asserts that the restricted mapping U to V has a differentiable inverse mapping V to U.